Hello, we are from Group 4 and today we will present about isothermal reactor design. Basically, this chapter is the combination of Chapter 1, which is about mole balance, Chapter 2, rate law, and Chapter 3, stoichiometry. Okay, for Chapter 4, we will use the knowledge of those three chapters and to evaluate the 5 steps method in order for us to design CSTR, BASH and PFR reactor. So now we will carry on with my friend Renuga. She will explain about the chapter 4. Okay, Renuga, please.
Alright, hi guys, glad you could join us here today. Now, let us talk about chapter 4, the isothermal reactor design. Can anyone tell me how many reactors there are there?
4.
Alright, can you name 2 of them?
CSTR, PFR.
Alright, very good. Now let us move on to the next one. There are 5 steps method in this very chapter. The first step is you must calculate the mole balances of each design. Next, you calculate their rate laws. Third, you calculate their stoichiometries. And fourth, you combine, and lastly, you evaluate them. This method is your mantra. You better get them. Let's look into a batch reactor. A batch reactor is used to determine the kinetics of a reaction under lab scale condition. When I say lab scale condition, it comes to your mind that this is used mainly in a small scale matter. This is a typical diagram of a batch reactor. Now let's see the designs of a batch reactor. Let's say a reaction of 2A that gives us B and C. And we are using A as our reference. First step, we do our mole balance. This we have already learned in our chapter 1 and 2. Next, we calculate the rate law. And third, we equate the concentrations of species A and B in terms of species A. Step 4, we combine the following rate laws and also the stoichiometry. And lastly, we evaluate to get this design equation. Now, using this graph, can anyone tell me how can we evaluate the rate constant? Anyone?
Using the slope of the graph.
Yes, a good guess. As you can already see here, that this graph gives us a good picture, and from the slope we can get the rate constant. Imagine a second order reaction. We can calculate the time of reaction using this specific equation. And in our first order reaction, we have to use that equation. Remember this, a first order and a second order reaction is totally different. So both comes along with different equations and different consequences. Now let's move on to a CSTR. This is a design of a CSTR. We use the same 5 methods. First, we check out the mole balance, and then we continue with the rate law, and then we find the stoichiometry, which is the concentration basically, and then we combine, and lastly we evaluate. As you can see here, in the batch reactor, we determine this as NA0, but here is an FA0. This is the difference. You have to pay attention. Now, we can also calculate the CSTR using the Dem-Kohlher number. The Dem-Kohlher number is a quick estimate on the degree of conversion in a flow reactor for a reversible reaction. Always remember, it's always a reversible reaction. If your Dem-Kohlher number is less than 0.1, then your conversion will be less than 0.1. But if your Dem-Kohlher number is greater than 10, then your conversion will be greater than 0.9. Therefore, we can define Dem-Kohlher number as a reaction rate over a convection rate. Please pay attention to this, it's very, very important. Now let's go to the recap. Okay, for a single reactor, is this applicable to a batch reactor or CSTR?
CSTR.
Yes, why?
Because use the FA0.
Yes, very good. In terms of space-time, what can we represent this term as?
Tau.
Yes, very good. We can represent space-time in terms of tau. And always remember, in a first order reaction, the Dem-Kohlher number is equivalent to tau times your rate constant. And in your second order reaction, is the same, but you must add the concentration, the initial concentration. Okay, good people. Let's move on to CSTR in series. Okay, CSTR in series. Very simple. The first CSTR, the exit of the first CSTR will become the inlet of the second CSTR. That is your series. From the mole balance, you can get the concentration at the exit of the first reactor, which is here. And then you get the reactor concentration of A at reactor 2's exit, which will be our end product. And the total number of concentration will be this plus with this, which will give you this. And this is only valid for the first order reaction. Now let's talk about parallel. In parallel, you can see that the conversion is the same. That means x1 equals to x2 equals to xn. Depends on the number of CSTR. And then we have the reaction rate, which also equals to the same. Therefore, the volume of an individual reactor is equivalent to the number of volume over the number of CSTR. And we have our molar flow rate. So, from this, from individual reactor volume, we can tell that everything leads to a single volume. Now we go into tubular reactor. Okay, I'm pretty sure all of you learned did RTD in your unit of, right?
Yes.
So you all should be familiar with this. It is usually used for gas phase reaction. We assume that a PF plug flow behavior with no pressure drop and no heat exchange with the surroundings. This is your differential form and this is your integral form. This is in the notes that I gave you in chapter 2. And this is a typical diagram of a plug flow. It can also be in a vertical position or a horizontal position. Now, for the plug flow reactor is divided into two. We have a liquid phase reaction and a gas phase reaction. Both is the same thing. Always go back to your mantra. First thing, your mole balance, and then your rate law, your stoichiometry, you combine, and then you solve. But since this liquid phase in second order, you can express this in terms of the Calder number. And in your gas phase reaction, if your temperature and your pressure is constant, then you can use this equation to find your concentration. The epsilon here is actually known as expansion factor. But if in your second order reaction, you can use this equation. Alright, so we have come to the conclusion of chapter 4. So I believe that if you have studied and answered, listened to my lecture, and if you do a little small working with me, you will understand this chapter better. Okay, so now I will go back to Hashir. He's our GA. He will come up with a small class exercise to ensure that everyone can understand this chapter 4.
So today we are going to do a small class activity in which we will recap what we have studied before. So what are the 4 steps we have studied? The first one is which is mole balance. Second will be rate law. Can you tell me what will be the third?
Stoichiometry.
Yes. And the last will be, we will combine all these 3 steps together to form one equation, which is basically combine and evaluate as well. So first I'm going to do with the first part, which is the mole balance. As we have studied this already in chapter 1, so I'm going to write the first equation for CSTR. V is equal to FA naught X minus RA. This okay?
Yes.
So now we'll go for the batch, which is now for the last one, it's PFR. After doing this, I would like someone to come and do the rate law. Anyone?
So rate law for CSTR. I think it's this one. that's for CSTR. For batch, there will be
CBCC.
okay. It's for batch. Now for PFR. PFR is the easiest one. So, is it correct, sir?
Yes, sir. Okay, Anwar, as I can see, everything done by Anwar is correct. Now I would like for the next part to someone to volunteer for the next part as well.
Amira, you go.
Amira.
Okay, for CSCR and PFR, the formula for stoichiometry is the same. And for batch 1, batch reactor,
Okay, we are done with step 1, 2, 3, and now the last one is combination and evaluation. And I'll ask Amar to do this part as well.
Okay, for combine and evaluate, we just combine the whole mole balance, rate law and stoichiometry into one equation. So for CSTR, the combined equation will be is correct, yes. So for evaluation, we just substitute the value for each, then we calculate the volume. And it's the same for batch and PFR. So I hope you can do it.
So after we have seen this example, but as if you want any more examples, I will be posting a link in the description of our video. So you can go to the link and actually see some questions, real questions with some solutions in the page. So I think that will help you for your finals and the upcoming test too. So I hope you can benefit from that, and good luck for your test too.